Hello, and welcome to Pioneering Proofs. In this video, I'm going to derive the conservation of energy, using nothing more than Newton's laws, the definition of work, and a little multivariable calculus. And upon navigating through the math, we will also encounter the work-kinetic energy theorem. So this proof for the conservation of energy can apply to 1 dimension, 2 dimensions, 3 dimensions, and even 4 dimensions and beyond. So it could really apply to really any spatial dimension. But here I'm going to construct a 2-dimensional diagram to help you visualize what is going on here. In this diagram, we have the x and y axes, as well as a position vector that we will call r. We have some one-dimensional path parameterized by t. In this case, t will be equal to time. And then we have our vector field that we will call f, and it will represent the force field. Therefore, we can describe all vectors that lie on our path as f of r of t. In this diagram, the vectors in the vector field, f, that lie on our path are blue, whereas the vectors that do not lie on the path are gold. But in this proof, we will focus only on the vectors in our force field F that lie on our path, as seen here. Okay, so work is the sum along the path taken by a mass of all tangential components of force exerted on the mass by the surrounding force field multiplied by distance that the mass travels. In the language of math, this is the integral along the path taken by the mass of the dot product of force exerted on the mass by the vector field F and the differential in the position vector describing the path of the mass. In terms of the diagram, this is the integral in time from a to b of the forces at all positions described by r of t, dotted with the time derivative of r. Since we are assuming that mass is constant, the force along our path is equal to the mass of our object multiplied by its acceleration, where acceleration of our mass is the differential in its velocity with respect to time. We can then bring the mass out of the integral since it is a constant, and recognize that the differential in the position vector of our mass with respect to time is the exact same as the velocity of the mass. We can then cancel out the time differentials and express the integral in terms of velocity. And so the resulting dot product is the sum over each component of the velocity vector of the ith component of the velocity vector multiplied by its corresponding differential all the way up to the nth component. So we're saying that there are n components because of the velocity vector because we want to keep this proof general so that it can apply to any number of spatial dimensions. Okay, so then we can move this summation over to the outside of the integral and then evaluate it. So here we can see that we are already beginning to get something that looks like kinetic energy. Now, all we have to do is recognize the crucial step that the sum over all square components of the velocity vector is equal to the square of the magnitude of the velocity vector. And then we can obtain the formula for the difference in kinetic energy of our object between times A and B, which is half of the mass of our object multiplied by the difference in the squares of the velocities at the different time points. So we can also look at work from a different perspective. If we apply the fundamental theorem of line integrals to the work equation and assume that the force field can be expressed as the gradient of a scalar potential function, which we will call phi, then we can see that the work is also equal to phi evaluated at time b minus phi evaluated at time a. In physics, we call this the difference in potential energy. So we have two paradigms of work. The first one is that we have work as a difference in kinetic energy, and the second is that we have work as the difference in potential energy. Now let's equate these two paradigms of work and perform some algebraic manipulation. And so we see that 1/2 of mv squared evaluated at A plus phi of A is equal to 1/2 of mv squared of B plus phi of B. This means that the sum of kinetic and potential energy at A is equal to the sum of kinetic and potential energy at B. And this is what we call the conservation of energy. Okay, so this proof was inspired by an excerpt from my Calc 3 textbook. And in there, the proof ends here. But something that I noticed is that the formula that we derived is based on 3 major assumptions. And here they are. The first one is that the mass is constant. The second one is that the magnitude and direction of the force field vectors do not change with time. It was just the position of our object that changed with time. And 3 is that the vector field is conservative, meaning that we can express the work as the change in scalar potentials. So I decided to see what happens when we let go of all 3 of these assumptions and see where the math takes me. So I'll admit that at this point I'm not really sure what I'm doing really, but hey, let's see what happens. Okay, so first I'm going to start by trying to rederive the kinetic energy equation without the previous restrictions. So notice that our vector field is not only a function of position, which is parametrized by time, but also a function of time itself. We also cannot say that force is simply equal to mass times acceleration, because mass is no longer constant and is a function of time. So force is equal to the derivative of momentum with respect to time. And if we use the product rule, okay, so we use the product rule. This means that force is equal to mass times acceleration plus velocity multiplied by time derivative of mass. And upon further simplification of the equation for work, we obtain this equation that I think would be the equivalent of the change in kinetic energy term that we saw before. So I guess I'll call it the I don't know, the change in kinetic energy equivalent. So now let's see what happens when I try to rederive the formula for the change in potential energy. So actually we can no longer do this because the idea of potential energy relies on the fact that for a certain subset of vector fields, we can express them as the gradient of a scalar potential function. But we are not, so we are assuming that we cannot always do this. Therefore, we will simply say that this term is equal to work. So if we again equate our 2 paradigms of work, then we can see that the work performed by the force field on our mass is equal to our change in kinetic energy equivalent. So this means that if we bring back the assumption that mass is constant, then work is equal to the change in kinetic energy. So what this tells us is that in order to be able to apply the familiar work, kinetic energy theorem, the force field does not necessarily have to be constant in time. And the force field also does not necessarily have to be conservative. So before concluding this video, I took a look at the minute physics video on the same topic. And it mentioned something called Noether's theorem. Now, I never learned about this theorem, at least not in my undergraduate courses in engineering, but my intuition tells me that we are kind of on the verge of proving this more general theorem about the conservation of energy. So maybe I'll try to learn more about this Noether's theorem and do a part 2 for this video. This has been Pioneering Proofs, and thank you for watching.